In this video, I will be discussing about circles bisecting the circumference of two fixed circles. So, when you first read this topic, you feel like, what is this nonsense? But this is coming from one of my students who asked me this question. And the question goes like, the locus of center of circle which bisects the circumferences of the circles this and this. There are two circles, and then you have to find a circle which bisects the circumference of the two fixed circles, and you can vary the circle which does this. And how does the center vary? On which path does the center of that circle vary? It's a question of locus. You have four options here, but at first when you read this question, when I read this question, I said I will need some time to think about it, what it means, because maybe we can do a little bit of coordinate geometry and accidentally land into the solution. But let's dive into it. What is it? What's the geometry behind it? So first of all, let's think about two circles. We know that if you have two circles, then there could be many cases, like they could be touching, they could be intersecting, they could be touching from inside, or they could be completely inside each other. So let's think about the intersecting case, because in the intersecting case you have many. I think this is more general. This case is more general in a way, because it has some more points to start thinking from. So we have this case, and we have the center of these two circles. These are the two fixed circles, and we have to find out the circle which will bisect the circumference of these two circles. Well, first let's look at the obvious geometry involved here. You have these two, another very two important points, the points where they intersect these two circles, and you of course have these centers. And when you join these lines, it's very easy to prove that they are perpendicular, and because you get these two congruent triangles, SSS congruency, and you get these two congruent triangles. That's why you get these two angles similar, equal, these two angles equal, and then you also get these two congruent triangles. That's why the lines are perpendicular. Okay, and then let's think about this. I am Before we find many circles which bisect the circumference of these two circles, we have to find at least one. So let's first see a circle which will bisect the circumference of these two circles. So if you search a little, then you will figure it out that you have to figure out, take this point, these 2 points. What are these 2 points? The diameters from the point of intersection. So let's not think about the second point of intersection. Let's not think about it now. Let's first think about the first point of intersection, and then from here you can draw two diameters, right? And these are the two diameters. And now it's a very interesting thing will happen. If I join these two things, you can feel that it can pass through this point, but are you sure it will pass through this point? So yes, it will pass through this point. Why? Because you see, if you have this angle here, this is an angle in a semicircle of the smaller circle, and this is 90 degree. And if you see this angle here, this is an angle in the semicircle of the larger circle, and this is 90 degrees also. So this is complete angle is 180 degrees, so this should be a straight line. So we have this triangle, and you need, like, it's a very common fact that from a triangle, from the corners of a triangle, like this triangle, the bigger triangle here, we can draw a circle which will pass through these 3 points, right? That's called the circumcircle of the triangle, and that is one of those circles which will do the job of bisecting the circumference of two fixed circles. So this length and this length is same, right? So the green circle has bisected the smaller white circle, and also this length and this length is same. For obvious reasons, and the green circle has also bisected the bigger white circle. So we have got a circle, and if you look closely, you will find another such circle on the other side, like these. Yes, so we have found two circles which does this job. Now let's move forward and think about the third circle, because you can't get any much insight from just two solutions, but those two solutions are very good solutions. They're very obvious solution from the obvious points in that geometry. But let's think about the more general case. So in the more general case, if I have to bisect the circumference of the smaller circle, I need two diametrically opposite points, right? And the circles should pass through these two diametrically opposite points. And similarly, I need two diametrically opposite points on the bigger circle, and the circle should pass through these 2 points also. So we have to find these 4 points like this, which can be concyclic. The property of 4 points being concyclic, it's not a very simple property to apply algebraically, or even in geometry it's not very simple to deal with such kind of a situation. So I am not going to use any direct formulas or anything like that. Let's dive into it. So if these four points are concyclic, so let's first think about the circles which will pass through the first two diametrically opposite points, which means this one and this one. If a circle passes through these 2 points, then this line will be the chord of that circle, and the center of the circle will lie on a line perpendicular to this chord and bisecting the chord. So any circle which passes through these 2 points will have a center on this line, right? Similarly, let's think about the other side. Any circle which passes through these two points will have this line as the chord, and the center of the circle should lie on the perpendicular bisector of the chord, so the center should lie here. So you get a point, right? We get a point, and maybe this is the point, but no, because the center should be here. The center of the circle which passes through these 2 points and these 2 points should be here. But is it the same circle, right? Is it the same circle? To check that, we need to check the radius. So this radius and this radius, and they don't seem same, right? These two radii are not same. You can draw a circle with green radius, and this center, the radius which is equal to the green line, and this center, and that circle will pass through this point number 1 and 2. And you can draw another circle with the red radius, let's call it r dash, and it will pass through these 2 points, let's call them 3 and 4. And if r and r dash would have been equal, then we could have got the circle which will have passed through all these 4 points, 1, 2, 3 and 4. But now you see that these two radii are not similar, not equal. That's why if I draw, let's say if I take the red radii, this one, and draw a circle from this center, I don't cross through these 2 points. I do cross through these 2 points here, but I miss these 2 points, and we have to take these 2 points into account also. So how do we do that? So we can apply the condition now, but I will show you that it's possible, it's not impossible. Let's see in the next diagram. Like if I adjust the diameters in this fashion, and then I get this point, and now I have the red and the green line which are of equal length, so I get a circle. So this is a more general solution. This is the third circle which we have got, but this is not the third, this is the road to infinity. What is the condition which we are using here? So the center of the circle which is bisecting the circumferences of the two fixed circle should be here. If that, let's call this as L, because we have to find the locus of this point. So let's call this point L. And what you see that the green line and the red line should have equal length. Let's call this length X. And then you can see that these 2 points, let's call them A or B maybe. Just a minute. Let's call this A and B. So you have these radius R1 and this radius r2, and this distance as x, and this distance as x also. And now you see that the C1L distance, this one is root under x square minus r1 square according to Pythagoras, and the other distance, the C2L distance, is this one. And if you square and subtract these two distances, you get a constant value r2 square minus r1 square. And this is it. This is the condition which we are looking for. And if you apply the distance formula here, then you will get the locus. So at this point, you can use the coordinate geometry to get the required locus. And how to apply coordinate geometry here? So C1L, let's call this L, the point L as xy, and this center as x1, y1, and this center as x2, y2, and this is a general point xy. So we write C1 L square. How do we write that? X minus x1 whole squared plus y minus y1 whole squared, right? Minus C2 L square. C2L. C2L is this distance. So you have x minus x2 whole square minus y minus y2 whole square, and that is equal to r2 square minus r1 square. And then if you solve this equation, you see that the x square terms will cancel out and the y square terms will also cancel out. You will get a linear equation, and that would be a line basically. So you can figure it out, the line. But as soon as you start doing algebra, you lose the connection with geometry. So I will show you geometrically what is that line which we are thinking about here. And that line, to figure out that line, I am joining this C1 and C2, and then I am drawing a perpendicular from L to this line C1, C2, and then I am rephrasing the equation. Let's call this point D, and then I write C1L square minus C2L square is equal to R2 minus R1 square as before, the condition which will give us the locus. But if I expand the C1L square, if you look at this distance, the C1L square, according to Pythagoras, it should be C1D square plus DL square, and the C2L square, this distance, according to Pythagoras, will be sum of C2D and DL. And if you do that, then in the next step, you see that the DL and DL cancels out, and then you see that C1D square minus C2D square is constant. I don't even need this R2 minus R1. This is a constant term. This is not a negative term. This is a constant term, because you see that the radius R2 is positive, is greater than R1, right? In this diagram, I haven't done anything. I get this result that this thing is positive. So I can say maybe positive constant. So C1D square minus C2D square is a positive constant, and if I do this A square minus B square factorization, I get C1D minus C2D plus C1D plus C2D is equal to constant, and C1D plus C2D is another constant. It's C1 C2. So let's include that with the constant on the right hand side, and what we get, that C1D minus C2D is constant. Okay, what does that mean? That you can't move the D, because if you move the D, then C1D and C2D both will change, right? And C1D will decrease. Let's say if you move the D on this side, C1D will decrease and C2D will increase, right? And this will give you a different C1D minus C2D, right? For example, you have 10 minus 5, and this term here 10 decreases to 9, and this term here, this increases by the same value, let's say 6, then you get a different sum, right? So you can't move the D, and if you can't move the D, what is D here? D is the foot of the perpendicular of the point which we are looking for on C1, C2, and if you can't move this D, which means that you should be on the perpendicular line from L to C1, C2, like this. You see, this is the locus which we are looking for. It might take a while for you to understand all of these, so you can rewatch this video and you can think on your own and decipher what I just said. But I believe what I said is correct. So this is the locus which we are looking for. Okay, so let's now come back to this question. The locus of the center of the circle which bisects the circumferences of these two circles. These two circles, if you plot, you will get them like this. This is the first circle. X square plus y square is equal to 4. The smaller one and the bigger one, it has a center at 1 comma minus 3 and a bigger radius which you can figure out. So if you plot them, they look like this. You can figure out the radius as 1 plus 9 minus 1, 3. This has 3 radius. This is 3 and this radius is 2. Anyways, so we have these two circles and we have to find the center of the circles which bisect the circumference of these two circles. So let's revise what we learned here. So how we're going to do it? We will of course figure out the important points here, like these 2 points where the circles intersect, and we will join C1, C2. Okay, and then we will find out the first circle which I discussed in the starting of the video. The first circle I can draw by making the diameters from a point of intersection. You make a diameter on this circle, you make a diameter on this circle from the point of intersection, and then complete the triangle. And everybody knows that a triangle has a circumcircle, and that circumcircle you can figure out by drawing perpendicular bisectors. You figure out this center and this is the circumcircle. So this is the first circle which we have, and we figured out that the center of the circle, from the center of the circle, if you draw this perpendicular, this is the locus. This blue line here is the locus. It's perpendicular to the line joining the centers, right? And the foot of perpendicular, this was the D in the previous slide. This D should not change. So you can have the center of the circles anywhere here on this line. I will also verify it for you. Let's take a random point somewhere here. This is a random point, and I can show you that I will draw a circle from this point which will bisect the circumference of the two fixed circles. Are you ready? Yeah, so what I do, I connect the center and this point, then I draw a diameter. I connect these two centers, and then I will draw these two diameters on both the circle which is perpendicular to this line. Okay, and then I will mark out the points where these diameters intersect, like here, and you will see a point appearing here, a point appearing here, and here. Let's go. Yes, yes, yes. And these are the points through which our circle would pass, and it would bisect the circumference of these two circles. So thank you very much for watching this video. And mathematics is interesting. What is the use of this kind of a thing? I don't know. Thank you.